Welcome to homework.
So in this question, we need to deal with a spectroscope. It's actually more frequently, the common name for it is actually spectrometer. Um, so the setup or the device, you can probably see a picture of it if you read section 7 of chapter 24. But what happens is that it has a grating here. And then the light passes through, and then it exhibits diffraction pattern at the back of it. So assume this is a pattern by the light. And then what you do is you observe it at different angles. So say if you observe it here, you will see the central maximum. If you observe at different angles, you can only see the light when it is at the maximum. So you can only observe the light at certain angles. And that angle will tell you what wavelength the light is. So it is a device used to measure the wavelength of the light. So in this case, we have two spectra on each side of it. So we have 26. These two are obviously the two spectrum for the same light because they're all roughly 26 degrees. And then these two are the spectrum for the other wavelengths. But I guess the problem is they're not exactly the same. You expect the angle to be the same on each side of it. And that's because it's an experiment, and experiments more or less have some error associated with it. So we need to find a way to cope with the data. So let's first observe it a little bit. I think there is a negative sign here. There are a lot of ways you can use to handle the data. What I would be doing is to just take the average. And that can be done, or I guess when I say take an average, what I mean is because one is negative and one is positive, what I mean is that I will try to subtract the difference. I try to get the difference between these two angles and I divide them by 2. And by doing that, what I am correcting of this experiment is I am calibrating the center line. So if it's 26 degree, 38 minute for this one and 28 degree 18 minute for this one, what I'm assuming is that they are different because the central line is a little bit off the center. So I will correct it by taking the average. But that is one strategy I'm using. You can use different strategies to deal with it. I can't immediately think of another better one, but it shouldn't be it's not a unique way to deal with this data. There are a lot of error correcting algorithms you can use in experiments. But let me first do this for the 26 degree one. It's on each side of the center. I'm calling one of them up, one of them down. And I just assume the negative ones are the angle down here and the positive ones are angle up here. So I call it theta up minus theta down over 2. That is 26 degree 38 minus 28 minus not negative 28 6 degree over 2. Okay, so that is 26 degree 28 minute. So now it's time to go back to our diffraction grading problem. We have d sine theta equals lambda times m, but we're looking for the first order, so m equals 1, and that gives us lambda equals d sine theta over m equals 0.01 centimeter over 9650. That is the separation between the slits times sine 26 degree and 28 divided by 1. This gives us 4.618 times 10 to the negative 5 centimeter. Oh, sorry, this really should be meter. So, sorry, just typo. This is meter. 0.01 meter is 1 centimeter. So this is 461 nanometer, or 462 nanometer. So this is a wavelength of the light. We can see it's roughly blue light. And some calculators may not accept this notation. Some calculators may only accept the degree notation. So in that case, what you have to do is you have to translate this degree and minute notation into degree notation. So we know 1 minute is 1/6 of a degree. So it's 26 plus 28 over 60, 1/60. So that gives us 26.47 degree. Yeah, so just in case your calculation does not accept the notation, you will have to convert it to degree, to 26.47 degree. But anyway, that is the wavelength corresponding to the 26 degree angle. Now we have to work the other wavelengths that is associated with the 40 and 41 degree. And again, we have up minus down over 2. So that is 41 degree over 2 minute minus negative 40 degree 27 minute and over 2. This gives us 40 degree and 45. And the lambda can be found by using, I'm going to call it lambda prime to indicate that it's different. And that is, again, 0.01 meter over 9650 times sine of 40 degree 45 minute, or if you convert it, it's 40.74 degree divided by 1. And that gives us 676 nanometer. And so this is red light. So you have roughly a full spectrum over here, from blue light to red light. And yes, calculate wavelengths based on these data. That is the two wavelengths we get. And that is the range of the spectrum.